Hello, and welcome to another Common Core Geometry lesson by eMathInstruction. My name is Kirk Weiler, and today we'll be doing Unit number 9, Lesson number 4 on intersecting chords. Now, as we've learned previously, chords are simply line segments whose two endpoints fall in a circle. And since they're line segments, not lines, right, they can certainly be parallel, but they can even be non-parallel and non-intersecting, right? But when two chords in a circle intersect, interesting things happen in terms of both the angles that are created by the intersecting chords and the way the chord lengths get partitioned when they cross each other. And that's what we're going to explore and prove in today's lesson. So let's jump right into it. All right. So we've already kind of reviewed this. A chord is any segment that has both endpoints on a circle. So AB in this case is a chord. What's remarkable is what happens when we have chord AB and let's say chord CD that intersect, that cross each other. And here it goes. Intersecting chords. The angle two intersecting chords form is equal to 1/2, that looks familiar, 1/2 the sum of their intercepted arcs. Well, a picture would be helpful here. Let's take a look. All right, so here we've got chord AB and chord DE, and they're intersecting at F. Now, please note, there's actually four angles here, right, that are created, right? There's angle DFB, angle BFE, angle EFA, and angle AFD. But of course, due to the fact that there are vertical angles, the angle here and the angle here are equal. DFB is equal to, AFE, right? And BFE is equal to DFA. But what does it mean to be 1/2 the sum of their intersected arcs? Well, let's just talk about angle DFB and AFE. These two angles intercept arc BD and arc AE, right? So what we see is that those common measures, right, can be found by adding the two arcs together and multiplying by 1/2, or, adding the two arcs together and dividing by 2. The angle that that chords make, and of course I'll have to tell you which angle I'm talking about. Am I talking about this one or this one, right? Will be 1/2 the sum of their intercepted arcs. Now we haven't proven this at all right? But that's going to be part of what we'll do in today's lesson. Okay, let's take a look at this particular problem. All right, here we go. Exercise number 1. Given circle O shown below with chords AB and CD intersecting at E, what angle is congruent to AED and why? So what angle in this picture is congruent to AED? Pause the video now and write it down and explain why. This should be pretty easy. All right, well, AED, which is right here, will be congruent to angle CEB or BEC because they are a vertical angle pair. All right, letter B. What two arcs do AED and your answer to A, CEB, intercept? Highlight them on the diagram. Why don't you go ahead and do this? All right. Well, let me highlight them in a thicker brush stroke, right? They intercept arc AD and arc BC. Now, you might think that that's kind of a silly exercise, but for some students, that can be very difficult. When we talk about two chords and these angles, the actual arcs that they intercept can be kind of tricky for students. So now, let's go down to here. Now, right now, we have not proven this theorem yet, but we're going to use it. We will prove the theorem in just a little bit. Okay, in the next exercise, we're going to get into it. But let's take a look at letter C. It says if the measure of the smaller of the two arcs in B is 58 degrees, and the measure of the larger of the two arcs is 76 degrees, find the measure of angle AED. All right. Well, Let's just say that this is the smaller arc. It certainly looks like that. And this is the larger arc. All right. Then what the theorem says, very simply, is that the measure of angle AED is equal to 1/2 of their sum, 58 degrees plus 76 degrees. All right. Of course, we can use our calculator or just, our heads to add up the 58 and the 76, and we get 134. And then, of course, we can divide by 2 to find half of it, and we find that that is 67 degrees. So it's a relatively easy theorem to use, especially in that direction. All right? Let's take a look at letter D. It says, if measure of arc AC equals 61, then use the theorem above to determine the measure of arc BD. Check your work to see if all 4 known arcs now sum to 360 degrees. All right, so here's what I mean by this. All right, this could be a little bit tricky. I know right now that that angle is 67 degrees. I'm just going to throw this over here. Okay? So because I know that this angle is 67 degrees, I can figure out what angle AEC is by simply subtracting the 67 from 180, right? Just do 180 minus 67, and I find that this angle is 113 degrees. Now I've been told in the problem that arc AC is 61 degrees. Now obviously I could use that to then figure out what the measure of that arc is. But what I want to do is I want to use the theorem to figure out the measure of arc BD, and then use the fact that all 4 arcs should sum to 360 to check my answer here. So how can I actually do that? Well, I can do that by saying, well, the measure of angle AEC should be the measure of arc AC plus the measure of arc BD divided by 2. All right, so that's just another way of sort of writing down the theorem. If I take AC and BD and I divide by 2, that should give me AEC. Well, now look at what I know. I know AEC is 113 degrees. All right, I know that AC is 61 degrees, and I'm just looking for the measure of arc BD. All right, so the only thing I'm missing now in this equation is what I'm looking for, the measure of arc BD. And I can find it by multiplying both sides by 2. All right, 2 times 113 is 226 degrees. So now I have the measure of arc BD plus 61 degrees is equal to 226. So I can subtract 61 from both of that, and I find the measure of arc BD is equal to 226 minus 61, which is 165 degrees. All right. Now again, just, as a side note, you might say to yourself right now, gosh, I could have found that 165 much faster by taking the 58, the 61, the 76, adding them all together and subtracting from 360. Absolutely, hands down. I don't want to invalidate that. The point here really wasn't to find BD or to get that final answer. The point here was that many times when we use this theorem, the theorem that says that the measure of the arc made by the intersecting chords is 1/2 the sum, you oftentimes have to use it in this direction, i.e. they've given you the measure of the angle of the 2 intersecting chords, they've given you one of the 2 arcs, in this case arc AC being 61, and you have to find the other one. So again, we did this procedure because you'll have to do it. You have to do it on homework, you might have to do it on a test, etc. But now the beautiful thing is, let me bring this calculator over here. Actually, it's going to get all sorts of weird that way. Let me bring it right up here, make it a little bit smaller maybe. And let's take a look at what all these arcs sum up to. Let's do 58 plus 61 plus 76 plus 165 equals 360, right? So that verifies that the 165 must be right, okay? And certainly if this was just a problem where we had to find BD for no other reason but finding BD, I would totally take those 3 add them up, subtract from 360, and get that. I wouldn't do it this way. But again, you'll have to do this procedure this way, where you know the angle, you know one of the arcs, and you have to find the other arc. All right, so it's good to go through it. Let me step back just for a second, let you take a look at these, and then we'll move on and prove this theorem. All right, let's do it. As much as we can in this course, when we can prove a theorem, we should, all right? And this is going to go back to something we saw earlier in this unit. We're still pretty early in this unit, but let's take a look. Exercise number 2. In the diagram below, we would like to prove that the measure of angle GHE, which is this guy right here, that GHE is 1/2 the measure of angle arc GE, and actually let me highlight this, 1/2 the measure of arc GE plus arc DF, all right? So again, I mean, we could also prove it for these two angles here, but this is good enough, all right? So I'm going to prove that the measure of this angle is 1/2 the sum of the measure of those two arcs. All right, let's do it. First off, why can we say that the measure of the angle we're looking for, GHE, is the sum of the measure of angle D plus the measure of angle G? Why can I say that the measure of that angle right there, not so bad that it's highlighted, but I think I'll take it off, is the sum of that angle and that angle? Think about that for a second. All right, well that is the exterior angle theorem. I'm going to even capitalize it. It's a proper theorem. The exterior angle theorem. All right, remember, the exterior angle theorem, which is going to be very important in this unit. This angle is an exterior angle of this triangle, of triangle DHG, right? We've extended side DH. This angle is exterior to it, and it must be the sum of the two remote interior angles. All right? Using what we know about inscribed angles, though, what can you say about the measure of angle D? And what can you say about the measure of angle G? Write something down there if you can. All right, well, here we go. The measure of angle D, that inscribed angle, must be 1/2 of arc GE. So that must be 1/2 the measure of arc GE. And what can we say about the measure of angle G? Well, it's got to be 1/2 of arc DF. All right. And now, letter C says use the equality in letter A along with your results from letter B to prove the theorem, right? Well, what did we see? We said in part A, the measure of angle GHE, which is what we're trying to figure out, is equal to the measure of angle D plus the measure of angle G. All right. The measure of angle D is 1/2 the measure of GE. The measure of angle G is 1/2 the measure of arc DF. I can now factor a common factor of 1/2 out of both of those. Maybe we'll just put it right here. And we actually get what we're looking for. There it is. Right? The measure of that intercepted, or that angle created by the two intersecting chords, right, which is GHE, is 1/2 of the measure of the arcs that it intersects. And what's cool about that is that rests on two important things that we've learned previously in this course. One thing it rests on is the fact that an exterior angle is always the sum of two remote interior angles. That's this piece, right? And it rests on the fact that an inscribed angle will always be 1/2 of the intercepted arcs. Sorry, I can't talk here. So we've proven it. And once we prove it, we can use it. So let's keep using it. Exercise number 3. Let's take a look. In the diagram of circle K, chords AB and CD are perpendicular. Awesome. And they intersect at E. If the measure of arc BD is 126 degrees, determine the measure of arc AC. All right. Well, you know the theorem now. You've played around with the problems just a little bit. pause the video now and see if you can work through this one. All right, let's do it. Well, let's make sure we know what we're looking for. We're looking for the measure of arc AC. I'm going to highlight that. Maybe I'll put it in green. Okay, I'm looking for the measure of this arc. All right. Now what I know is right? I know that the measure of angle DEB, not DED, that would be very weird. Measure of arc DEB, measure of angle DEB, oh, I really can't talk right now, DEB, right, will be 1/2 of the measure of arc BD plus arc AC, right? That's the theorem that we just had. This angle or this angle, right, will always be 1/2 the sum of these two. Fair enough. But we know the measure of angle DEB. That's 90 degrees. So we know this is 90, right? We know that the measure of arc BD is 126 degrees. And what's cool about that is it leaves us just what we're looking for, the measure of arc AC. So what do we do now? Now your instinct might be to distribute the 1/2. That's fine, you can do that. But you could also undo the 1/2 by multiplying both sides of this equation by 2. And that would give us 180 degrees over here equals 126 plus the measure of arc AC. Then of course we could just subtract a 126 from both sides, and that would give us the measure of arc AC is equal to 54 degrees. All right, and that's it. Let me step back, go ahead and copy down anything you need to. All right, let's keep going. Now, we had one relationship that related the angle that intersecting chords make with the arcs that they intercept. All right, the second intersecting chord theorem, though, has virtually nothing to do with angles, and it says the following. If two chords intersect within a circle, then the product of the partitioned segments of one chord equals the product of the partitioned segments of the other chord. Picture. Here we go. Right? So I've got these two chords, A, B, and C, D, and they intersect at point E, which now is inconveniently covered by the pointer. There we go. That's a little bit better. Now, what this theorem says is no matter how you draw the picture, as long as the chords intersect each other, then what will happen is AE times BE will equal DE times CE. The product of the portions of the segments will remain consistent, which to me is just remarkable. I mean, it's really, really cool that that's the case. Is it practical, or are there a lot of practical ramifications for it? Maybe not. But somehow, right, the fact that DE times CE is AE times BE, I think is just amazing. All right, so let's take a look at this a bit. Okay, here we go. Again, what we're going to do is we're going to use the theorem, and then we'll come back and we'll prove it. Using it is exceptionally easy, as we'll see in this problem. Exercise number 4. In the diagram of circle O, chords AB and CD intersect at E. AE is 6, okay. BE is 4. DE is 3. And we want the length of CE. I'll call it X. All right. Whoops, that didn't work. All right. And it's this simple, right? This theorem just says, okay, look, 6 times 4 is 3 times X. That's the whole deal with the theorem, okay? When I look at the product of the segments of these chords, it stays consistent, all right? So it's as simple as 3 times X is 6 times 4. 3X is 24. Divide both sides by 3. And X is 8. You know, there's nothing much that's really all that difficult about this particular theorem, right? But why it works, that's a whole nother matter. So let's jump into that. Let's prove this theorem. And this is awesome, okay? Because it goes back to our unit on similarity, and we'll see why right now. Exercise number 5. Given the same diagram as in exercise 4 with a few extra segments drawn in, answer the following. All right, so just keep in mind, this is exactly the diagram we just had. We had AB, we had CD intersecting at E. The only difference is I put this segment and this segment in. That's it. That's the whole reason for those. But it's important because in letter A, it says give an argument for why ACE and DBE must be similar triangles. Why is this triangle and this triangle similar to one another? Take a minute and try to explain that. All right, well, this is really, really cool. Watch this, right? Angle A must be congruent to angle D. In fact, I'm going to mark that. These two angles have to be congruent, all right, because they both intercept, nice, they both intercept arc BC, right? They both intersect this arc. And remember, two inscribed angles that intercept the same arc have to have the same measure. But likewise, angle C must be congruent to angle B. Well, that didn't work. Angle C must be congruent to angle B because they both intercept arc AD. Well, at least it was consistent there. By the time I'm done recording Common Chord geometry lessons, we'll know exactly why that works. But that means that triangle ACE is similar to triangle DBE by the angle theorem. So those two triangles must be similar. Now, you wouldn't be incorrect to note that there's a third pair of angles that are congruent due to the vertical nature of those two angles. But I kind of like having those two marked alone because the reason that those pairs are congruent is based exactly on something that we saw earlier in this unit. Two inscribed angles that intercept the same arc must have the same angle measure. Now, let's prove the theorem. Now remember what the theorem says, right? What we really want to get to is we want to prove this, right? We want to prove that if I take AE and I multiply it by BE, that's going to be the same as DE times CE. And remember those similarity proofs where we had to prove that a product was equal to a product? Well, here we go. Now, let's make sure that we see it right. I'm going to draw these two triangles. I want to keep that on here. These two similar triangles so that they're in the same orientation, right? A, E, and C. And I'm going to label these with those arcs, all right? And then the other similar triangle, which is D, B, E, all right? So let's set up a proportionality and then get it in that product form, right? So what can I say? Well, I can say that AE divided by DE, right? AE divided by DE is equal to AC, we'll get rid of that red mark in a second, divided by, not DB. Wait, no, well, it is AC divided by DB, but I don't want AC involved, do I? I want that other length, so I want CE divided by BE. What I was about to write down wasn't wrong. It just wasn't going to get me that product, right? So AE divided by DE is equal to CE divided by BE. That's the fact that, right, that sides are proportional in similar triangles. But now using the product of the means is equal to the product of the extremes, I can now write AE times BE is equal to CE times DE, right? The product of the means is equal to the product of the extremes. So this theorem about the partitioning of line segments, or the partitioning of chords when they intersect in a circle, is a direct result of the similarity of triangles, specifically those two triangles. Isn't that kind of awesome? There's no way we would have been able to prove that had we not built up the work that we did with similar triangles. All right, well, let me step back, think about this a little bit, and then we'll wrap up the lesson. All right, let's do it. So today, we got a little bit away from inscribed angles, although they certainly came up here and there. What we looked at was what happened when two chords intersect within a circle. And we saw two different phenomenons. One of the phenomenons had to do with the angles that were created by the intersecting chords, and the fact that the measure of those angles was always 1/2 the sum of the measures of the intercepted arcs. It's kind of tricky to say, actually. And the other theorem, which we looked at briefly at the end because it's so easy to use, is that when the two chords intersect, right, it partitions them in a way that the product of the partitioned segments of one chord equals the product of the partitioned segments of the other chord. Also not that easy to say. The really kind of remarkable thing about that second theorem was it's based on similar triangles. And we'll see that. That's going to be a common theme as we work through this unit. There's going to be a lot of similar triangles that come up that justify theorems about circles. For now, I'd like to thank you for joining me for another Common Chord Geometry lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.